Okay, yeah, sorry. Okay, so thank you. So for this second part, we will open a very big parenthesis to introduce the language of manifold with corners. So this will serve as the setting that we use to attack this question here. So without going directly to the abstraction of the use of manifold with corners, we will demonstrate the intuition behind such language through a very simple example, like an example that has nothing to do with, well, what we have been talking about for now. So the example is the following. So suppose we consider a family of functions on 0, 1 defined by fh of x is equal to x over x plus h. And we want to consider the limiting function when h goes to 0. So when h goes to 0, this gives the function f0 of x, which is 0 everywhere. 0 at x is equal to 0, and it's 1 everywhere else. So we had smooth functions for h different from 0, and then the resulting is not even continuous. And here we will say that fh degenerates to f0 as h goes to 0. All right. So now suppose, so this is the image of what happens. So we have these fh and which convert to f0. Now suppose we want to look at this from the opposite point of view. Suppose that we have f0 and we want to construct the family fh, which degenerates to f0 as h goes to 0. So the problem with that is that the knowledge of f0 alone is not enough, because f0 only keeps information on fh away from 0. So, sorry. So here we had the fh like this. And we have f0 like this. So if we notice here, f0 only keeps the information of fh away from 0, but everything that happens here, so this information is lost in the limit here. So one way of getting back that information near x is equal to 0 is to consider a second limit of fh, and this is a scale limit. So for that, we introduce a change of variables. So we denote x is equal to h times big S, x, h is the parameter here. And so for fixed x, we let h goes to 0. So we look at the second limit, the scaled limit here. So it's limit when h goes to 0 of fh, hx, and we call this g of x. And here gives us a second limit. So this is big X over big X plus 1. So intuitively, this means that f0 serves as the model of fh when h goes to 0 away from x is equal to 0, while g serves as the model near x is equal to 0. So if we look at this picture, so the picture is as follows. So here we have, this is the family of h of x. This is our normal limit when h goes to 0. This retains the information away from 0. This gives us the information away from 0. And this behavior here, after rescaling, we get it in this second rescaled limit. So if we want to do the opposite, if we have f0 and we're trying to construct the fh that uh, degenerates to F0, we need this second information of G, and we see FH basically as a sort of gluing of this F0 away from x is equal to 0, and G as a rescaled version of G near x is equal to 0. And depending on the rescaling, we get the FH, so we get a whole family. So this is the first idea to keep in mind here, is that we need this second information when we're trying to do the opposite. So we have a degenerating limit and we want to construct the family of smooth functions. Now, this whole idea of rescaling can be given a geometric picture. So this will be a different picture. So this rescaling x, small x is equal to h big X. This is basically introduction of some projective coordinates. So projective just because here we're saying that big X is small x over h. Which is also equivalent to the introduction of polar coordinates. So what we're saying here is that if we consider the product space, so this is x, this is the parameter h, so this big X will be the possible directions of going to 0. So where X represents each line of going to the origin 0, 0. And we're separating those directions. So basically we're saying that we're introducing like polar coordinates or projective coordinates near this points, point 0, 0. And each point on this face here is a value of big X. So this is for big X here. This is origin H and X. So what before was a family of functions fh of x, oh sorry. Now it's just a function of two variables, fh and x, and then the x, and then we resolve by this new parametric space here by introducing this polar coordinates around 0, 0. So as I said, geometrically, this amounts to replacing the point 0, 0 in the parametric space with a set of all possible direction towards that point. So this is the set of half lines. In this case, it gives a circle, an arc of circle. So again, there is a natural map between the two spaces. So this is the new space, and there is a map beta, which is just called the blowdown map. So what we're doing is that we keep all points here the same, just this new face here is sent to the origin. And the whole process here is called, so the pair MB and the map beta is known as the blow-up of the parametric space M. So blow-up of the origin in M. So this is, for people who knows algebraic geometry, there is a notion of blow-up in algebraic geometry, which is replacing a point by the possible directions towards that point. But this is a bit different in two ways. So the first of all, here we're considering real directions, not complex directions. And second thing here, we're separating half lines. We're not taking just the whole line. Like what we mean by direction is just a half line towards the point. But the idea is the same of what we call the blow. And as we noticed here, so naturally the resulting space has a structure of a manifold with corner. So a manifold with corner is just a manifold with points which are locally modeled on Rn minus k times 0, 1, 0, infinity to Rk. And so in our case here, we had, so already the product 0, 1, 0, 1 is already a manifold with corner, which has this two boundary hypersurfaces. So this is the boundary hypersurface defined by h is equal to 0. So in this case, we call h to be a boundary defining function for this for this boundary hypersurface, and this is the x is equal to 0. So this is a boundary defining function um, for this boundary hypersurface. And we're replacing this manifold with corner with another manifold with corner by adding a face. So we're replacing this corner by another face. And here we have three faces. So this we have this new face B, and this is H1 and H2. And here this B has different possible boundary defining functions, but one of them is defined by x squared plus h squared is equal to 0. So I take the square here because what we will mean by boundary defining function, so it's a function which vanishes only at that hypersurface, boundary hypersurface, but the derivative does not vanish anywhere on that boundary hypersurface. So it's like degree 1 in some sense. So, as I said, from this point of view, we no longer think of fh as a family of functions, but rather a function of two variables, f, h, and x. And the limit fh, when h goes to 0, is just the restriction of f on the boundary hypersurface. H is equal to 0 on the parametric space. And what we see from the limit, the fact that the limit is non-continuous, is that fhx is singular on the boundary hypersurface, h is equal to 0. And the blowup of the origin, so what we said, that blowup, resolves f, which means that if we look at the beta star f, which means f squared beta, this will be defined everywhere except from here, but it could be extended in a natural way by taking the limit. So the limit is well defined, and the resulting beta star f is actually smooth on this new function. So in some sense, this blow up here that we did served as a way of resolving f. So which was singular on the initial space is now smooth because the fact that there was no limit on x equals 0, after separating the directions, we have a limit. So the rescaled limit g from before is now just the restriction of beta star f to the new boundary hypersurface B. So this will be the whole new point of view of thinking of these degenerating problems. Another benefit of this point of view is that we can look at the regularity of F not only. So here we are saying that FH is smooth. So this means that it's smooth for each H, but we can look at derivatives in the other direction, in what I call here vertical derivatives. So we can study the regularity not only on each fiber, but also in terms of the degeneration parameter H, or the other boundary defining functions for the new phase hypersurface B. And in particular, we can look at asymptotic expansions in terms of these boundary defining functions. So in the example that we mentioned, F is resolved to be smooth on MB on the blown up space, and therefore it has asymptotic expansion near each boundary hypersurface, just given by the Taylor expansion, because it's just smooth. But in general, when we look at when we are working on manifold with corners, we consider a more general notion of regularity near the boundary, which is more general than just being smooth. And this is known as having polyhomogeneous expansions. So these are kind of like Taylor expansions, but different. So we define polyhomogeneous functions on a manifold with corners. These are functions which are smooth on the interior, so there is nothing. So in the interior, it's just smooth. There is no problem. But when we approach a certain boundary hypersurface, well, we suppose that we have an asymptotic expansion of which has, so if this is the boundary H, and we have a boundary defining function for H given by XH, then we suppose that we have asymptotic expansion of the type powers of XH and powers of logarithm of XH. So here the lambda and K, the powers are, so lambda could be complex. The K, the powers in the logarithmic powers are always natural powers. And we suppose certain, so here we call suitable index set. We suppose that certain conditions on the index set, in particular, the most important condition is that if lambda K, the norm, so the norm of lambda K, so norm of lambda squared plus K squared goes to infinity, this implies that the real part of lambda goes to infinity. So another way of understanding this is that if we fix lambda, there is only a finite number of terms of logarithm. So there is a higher, highest possible power of logarithmic power, and then other smaller ones. And there are no negative ones. And yeah, and it is in particular, this is also a discrete set. So yeah, there are some other conditions, but I will not mention them for now. But where another way of characterizing polyhomogeneous function is that, so for example, in the case of a manifold with boundary, we can take the Mellin transform near the boundary, and polyhomogeneous functions are the Mellin transform of meromorphic functions. So this should be thought of kind of like a real counterpart for meromorphic functions. So these basically allow certain types of singularities. So of course, as you can see, when xh goes to 0 means at the boundary, the logarithm goes to minus infinity. so these are singular at the boundary, but the singularity is controlled. And actually, in most of the important example that we consider, the complex the powers lambda here will be not complex, but they will be real, and not just real, they will be positive real, uh, positive real powers. So what's the point of look allowing such general notion of regularity? The main idea is that when we consider elliptic operators on manifolds with corners with a certain additional structure, the solution to elliptic equations with smooth initial data are not always smooth, but they are polyhomogeneous. So the most simple example is consider R plus, and we can consider elliptic operator given by x dx. So this is an operator. So we ask, for example, what is x dx u is equal to 1? Well, the simplest solution for that is just the logarithm. So x dx of logarithm x. So here would be x over x, and this is equal to 1. So even though 1 was smooth up to the boundary, the solution logarithm x is not smooth up to the boundary, but as you can see, it has the logarithm. And the general result in that sense is that, well, this is the only bad thing that can happen. So if we can start with something smooth here, like if we have an equation of the type PU is equal to V, and P is elliptic operator on a manifold with corner such that it is generated by vector fields which are smooth at the boundary. So this is the additional structure. Then usually when V is smooth up to the boundary implies U not necessarily smooth, but polyhomogeneous. But in general, V is polyhomogeneous implies U is polyhomogeneous. That's why polyhomogeneity is the right regularity to be considered. So this polyhomogeneous implies U polyhomogeneous. So this is the best regularity we could get in such a setting. So that's the reason we consider this notion here. Now we get to, after all this long parentheses on this manifold with corners, so just to give an idea why we care about using such a language, we get to the main theorem. So the theorem is, so suppose we have a conical Calabi-Yau, x0 with its conical Ricci-flat Kähler metric. And we suppose for simplicity, so this is not, so we can suppose that there is a finite number of isolated conical singularities, but just for simplicity, we suppose that there is only one singular point x modeled on a certain Calabi-Yau cone C. So as we mentioned before, and suppose x0 admits a Croupon's resolution. So in particular, the Croupon's resolution is local. So we suppose that the cone C itself has a Croupon's resolution. So if C has a Croupon's resolution C hat, we can produce the resolution of x0 by given by x hat, and this is just defined like x0 minus x sum with C hat, basically. So we suppose that we have a Croupon's resolution. Then under certain generic assumptions, these are some cohomological assumptions that we need for the x hat to be Kähler. So under certain assumption, there exists a family of smooth Calabi-Yau metrics, as we mentioned before, G, Cy, epsilon on the resolution, such that which degenerates to x0 with its conical metric. And moreover, uh, this family is polyhomogeneous in the sense that we explained before, in an appropriate blown-up space, blown-up parametric space. And of course, we have a similar result in the case of a smoothing. So this is the main theorem, which exactly says what we wanted. So what was algebraic process, now it's a metric process. We can see x0 as a limit of these Calabi-Yau metrics. And in addition to that, we have this polyhomogeneity. So the idea of proof, so as we saw before, we want to construct a family of smooth Calabi-Yau metrics on the resolution which degenerates to x0. And as we learned before, the information, just x0 alone is not enough. We will need a second model. So a model near the where the degeneration happens. So if this is E, this is the point X, this is x0, this is the resolution. So we need a second model near here. So we need another metric. So for that, first of all, we consider the parametric blob, the parametric space x hat times 0, 1. So this is x hat 0, 1. So 0, 1 just for the parameter epsilon. And here, this is the E, the subvariety which the inverse image of the singular point. And since we want a second model near this, as we saw before, the idea to be done is that we need to blow up this point. It's not a point; it's a whole subvariety, but basically the same thing. Instead of just that subvariety, we take all the possible directions towards that subvariety. We consider the blow up of E times 0 in this parametric space. And this will give us this new blown up parametric space. So for epsilon bigger than 0, these are just the fibers x hat. And when epsilon goes to 0, we have two models. So this is basically x0. And this will be our second model. And it looks like the resolution of the cone itself. So basically here we're saying that this is our x hat. And locally, after blowing up, we get something like the resolution of the cone C. And the cone C is the model cone of on x0. So, and here, if you know, if you notice there is this union with L. L is just a link of C. So here we have this resolution of the cone. So we have the cone C. This is the resolution of the cone, but it still looks like the cone at infinity. And this is the corner is just a link, and here this is basically attaching x0 or taking the singularity and adding the link instead of the singular point and attaching it with the resolution of the cone C. And now what we have is that, well, we have here the metric the conical metric on x0 here. And we need a second metric to be attached to it, to be glued to it on C hat. Well, fortunately, this exists. There is a result by someone called Goto, who says that a Crepont result. So if we have a Calabi-Yau cone, if C is a Calabi-Yau cone, and C hat is a Crepont resolution, then C hat has Calabi-Yau metrics, which are, now this time it's not conical, it's asymptotically conical, which means they look like the conical metric of C near infinity. So these look like the conical metric of C near infinity. And now the idea for proving our results is that so we start with the conical Calabi-Yau metric of x0, and we start with the asymptotically conical Calabi-Yau metric on C hat, the resolution of the cone, which we call omega C hat AC for asymptotically conical, and we glue them together. So basically we have this x0 with its conical metric. And this is C hat with its asymptotically conical metric. And now what we do is, well, we take away this part. We take away this part. We do a rescaling and we glue both. We glue the two. So that in the end we have something like this is part of x0 and then with a rescale. And this is a gluing region. So this is the part of x0 and this is the part of C hat with the rescaling, epsilon squared. And they could be glued together because, well, the metric of x0 looks like the tip of the cone, like uh, the vertex of the cone, and this looks like the cone at infinity. And after rescaling, we can glue both. And we can make sure that the gluing is made in a way such that the resultant metric is scalar metric. So this is not a problem. This could be done. So this will give us a metric omega epsilon, and on x hat, why x hat? Because that's what x hat is. It's just x0 plus C hat. And well, it is Ricci-flat here. It's a Kähler Ricci-flat in this part. It's Kähler Ricci-flat in this part. But we mess it up in a little bit when in the gluing region. So the resultant metric is approximately Calabi-Yau. It means that the Ricci curvature is almost zero, but it's not zero. But the error term vanishes when epsilon goes to zero because we just go to the conical metric of x0. And then we wanna solve the complex Mongeau pair equation to turn this into Ricci-flat. So before solving directly, we will improve the error by solving this complex Mongeau pair formally. So what means formally? That means that we plug the polyhomogeneous expansion. So why polyhomogeneous expansion? Because it's a guess, because in the Mongeau pair equation we have the linear part is elliptic, it's the Laplacian. And when we plug a polyhomogeneous expansion and we can solve term by term, this will allow us to improve the error term, and the error term now vanishes infinitely quickly. This means not only it vanishes when epsilon goes to zero, but also all of its derivatives. And we finish by solving the equation exactly using a Banach fixed point argument. So we use Banach fixed point theorem. We make sure that there is, like, we prove that we produce a contraction on certain weighted Sobolev spaces, and we use a Banach fixed point theorem to solve the complex modular pair equation. So basically that's what we do. So we start with the metric on x0. We start with an appropriate metric on C hat, which exists by another result. We glue them together. This is conical, this is asymptotically conical. We glue the infinity of this with the singular point of this. And then we improve the error term by polyhomogeneous expansion, and then we solve by the Banach fixed point theorem. So this part here, this step is actually not necessary. We can directly apply the Banach fixed point theorem directly here, but we do this to make sure that we have the right expansion that we want. We make sure that we actually have a polyhomogeneous expansion. So this is why we add this intermediate step. Because knowing how that we have polyhomogeneous expansion will allow to do analysis on this. So yeah, this is basically the idea of the proof and the strategy. And I will stop here, I guess.